is a city that should never have existed. Built on a fault line, it has always suffered from violent earthquakes and typhoons. And yet, with over 37 million inhabitants, it's the largest and most populated city in the world. Dynamic and modern, yet its millions of people live with a constant threat of earthquakes.
The next one could very well happen now, for instance.
The danger is invisible. No one knows when or where it may strike.
If Tokyo's hit, all of Japan goes down.
Stubborn and brave, the Japanese capital has adapted to the danger. Tokyo has put its ingenuity to work to develop the most earthquake-resistant structures in the world.
We have to be faster than the earthquakes to find ways to fight them. It's a race between us and earthquakes.
Since the city was founded, tireless builders have defied fate. As early as the 7th century, they mastered amazing techniques to protect their buildings and the city's inhabitants.
We build floors so they're very flexible and so they can move.
Despite the ground shaking on a regular basis, Tokyo has become one of the world's most powerful capitals. When quakes strike, its buildings sway but don't collapse. How is such a feat possible?
We've made flexible buildings that don't fight the movement. It's the story of the oak tree and the reed. The tree, no. The reed, yes.
On an island subject to natural disasters, Tokyo must also cope with typhoons and diluvian rains. Engineers have come up with a unique system to save their city.
We have pumps that can evacuate 200 cubic meters of water. In other words, the equivalent of a 25-meter pool every second.
But is Japanese ingenuity prepared to face the large-scale disaster looming on the horizon? A massive earthquake, the big one, which happens about once every 100 years.
There's more than a 70% chance that within the next 30 years, we'll be hit with a huge earthquake.
How have engineers managed to build the most modern city in the world on land that is constantly shifting? What new dangers does Tokyo face? How is the city preparing for the worst? Will Tokyo be able to withstand the wrath of the earth once more? Journey to the land of the rising sun. Chronicle of a megalopolis facing disaster. Japan's capital is unlike any other city in the world. Located on the main island of the Japanese archipelago, the urban area of Tokyo spans an expanse of 50 kilometers. Literally, Tokyo means Eastern Capital. It's the most populated city in the world. The Japanese capital is the hypercenter of a megalopolis that stretches 1,200 kilometers. Over 105 million people, in other words, 80% of the Japanese population, live on this strip of land sandwiched between the mountains and the sea. The city of Tokyo is a miracle issued from the determination of its inhabitants, who after each disaster have always picked themselves up and kept forging ahead. Because living in Tokyo means learning to live with the danger of natural disasters.
For us Japanese, it's part of our culture. In a way, we're used to calamity.
Every year, over 1 million earthquakes rock the earth, 100,000 of which can actually be felt by people. In Japan, about a dozen large earthquakes happen each year. One legend has it the large island rests on a giant fish that thrashes about every once in a while. Japan's high seismic activity is due to the fact it lies at the junction of 4 major tectonic plates: the Pacific, North American, Eurasian, and Philippine.
We know we have a sword of Damocles over our heads, or rather under our feet. Everyone knows it could happen, but we live with it.
The Pacific plate off the coast of Tokyo shifts westward 8 centimeters a year. This phenomenon, called subduction, is responsible for the Earth's most violent quakes. The plates come into collision and generate rising tension. One day, the friction unleashes a force that triggers a huge vibration. Scenes such as this are commonplace for the inhabitants of Tokyo. And things aren't about to change, because in the region of Tokyo, the number of earthquakes just keeps rising, and they can be very intense.
Intensity lets us accurately measure how, in every region, each place was shaken.
In Japan, seismic intensity is measured on the Shindo scale. It describes the degree of shaking at a given point on the Earth's surface. The higher the level, the greater the damage. At 4 on the Shindo scale, people are frightened. Most people asleep wake up. At 5, people find it difficult to move. Many unreinforced walls collapse. At 6, certain buildings lose their roof tiles and their windows break. At 7, walls collapse. The island nation suffers 20% of the most violent earthquakes on the planet. The city of Tokyo is built on a plain, a particularly vulnerable zone that rests on water-saturated soil with very low density.
As you see on this map, the red shows where earthquakes are biggest. Blue zones correspond to areas that don't feel too many quakes. It's ironic, but the places where it's easiest to build and live are the same areas that are most susceptible to earthquakes.
Nevertheless, this is where the Japanese decided to build their capital. The terrain is vast and flat. It also has sea access. But in fact, the Japanese couldn't have found a worse place to build their city. And yet. Formerly called Edo, Tokyo was originally a small fishing village that grew and gained in importance over the centuries. Most of its people lived in traditional, inexpensive wooden houses. With each earthquake, the small structures and their heavy thatched roofs would collapse. Tokyoites would tirelessly rebuild as they awaited the next quake. Still, Tokyo's builders would always put their ingenuity to the test. It was out of the question that important buildings like palaces or temples should collapse every time the earth shook. Japan's Buddhist temples are among the oldest wooden structures in the world. They are distinctive in that they've been built in a way that offers amazing resistance to the frequent earthquakes that rock the country. Starting back in the 7th century with pagodas, builders sought to erect increasingly taller structures and increasingly more solid ones. To do so, they perfected an ingenious technique.
The big wooden temples and shrines don't have foundations. Buildings are often set on enormous columns, then set on large stones that are barely sunk into the ground. Globally speaking, that's what defines construction in Japan for the past 1,500 years.
The central pillar of the pagoda is only attached at the top level. It's independent on the lower levels. Thanks to the central pillar, any distortion resulting from an earthquake is spread evenly over the 5 levels, ensuring the shock isn't concentrated in one spot where it could cause a rupture.
We've made flexible buildings that don't fight the movement. It's the story of the oak tree and the reed. The tree, no, the reed, yes. The building moves, like me, to absorb the shock.
This type of building has never collapsed. We can affirm that the system is very efficient.
Solid structures that can flex and sway. Once again, this was the principle used to build Edo Castle in the 15th century. To protect the palace, constructors built over 6 kilometers of moats and walls. Made of granite blocks weighing several tons and fit together like a puzzle, The wall does a remarkable job of resisting tremors. Once the shaking stops, the blocks settle back into their original spots. These jewels of Tokyo architecture have proven they can resist earthquakes. On the other hand, the traditional organization of the city with its small streets and wooden houses turned out to be unadapted. And Tokyo would pay a high price. Today, Tokyo is an ultra-modern city with a giant forest of skyscrapers to prove it. It's hard to imagine that over the course of the 20th century, Japan's capital suffered two major disasters that reduced it to rubble. September 1st, 1923, 11:58 a.m. The ground shakes. The Kanto earthquake strikes. 10,000 people are killed as buildings collapse. But the worst is yet to come. In the neighborhoods of wooden houses, over 200 fires break out simultaneously in different spots when thousands of braziers are lit to cook the midday meal.
And in 1923, an enormous fire razed a good part of the city. It burned people who couldn't get away because they were stuck in the rubble. People sought shelter along the rivers and were burned there.
Things went from bad to worse. A tsunami washed over the plain and dealt the final blow. Entire districts were ravaged by fire and flood. The death toll was mind-boggling, over 200,000 victims, and 2 million people were left homeless. Damage was considerable. Over 700,000 houses were destroyed. The traditional, disorderly urbanization of Tokyo, with its flimsy wooden structures and narrow streets, was blamed for the thousands of deaths. Practically 2/3 of the city had to be rebuilt.
It turns out that the few structures back then that were made out of reinforced concrete were still standing.
The Japanese government embarked on a vast rebuilding campaign to make concrete structures that wouldn't collapse or burn in the next earthquake. But 22 years later, Tokyo was destroyed once more. On the night of March 9 to 10th, 1945, 335 U.S. bombers dropped over 1,700 tons of bombs on Tokyo. It was one of the deadliest air raids ever, causing over 100,000 deaths. A third of the city was annihilated.
It would take Japan about 10 years to get the economic industrial machine back in motion and rebuild its cities. Because Tokyo wasn't the only city destroyed. Hiroshima and Nagasaki were as well. So the population of Tokyo started growing again in the 50s. And it hasn't stopped since. It's still growing today.
The Japanese had no choice but to rebuild their capital as quickly and inexpensively as they could. The city got down to business. Urban motorways, tunnels, vast building complexes. But turning the town into a concrete jungle didn't come without risk. In fact, it even had heavy consequences on the future of the city. Since concrete is watertight, it prevents water from soaking into the ground. The upshot? The sewers fill to the brim and water spills over into the streets, triggering new disasters. Because let's remember that several rivers flow through Tokyo and its region, and some areas of the capital are even built below sea level. Not to mention the fact the archipelago is regularly doused by torrential downpours and typhoons. Typhoons are tropical cyclones, one of the most powerful atmospheric phenomena that exist. The winds are devastating and the rains torrential, leading to flooding, rock slides, and landslides. Typhoon season is mainly in the fall. On average, 26 typhoons form in the northwestern Pacific Ocean each year, and more than a dozen of these curve toward Japan.
By its nature, a typhoon already means heavy rains. But in Japan, twice a year you have the rainy season. If typhoon rains combine with those of the rainy season, it means extremely heavy precipitation that leads to mudslides and makes rivers overflow. And this causes a great deal of damage.
We also have highly concentrated rainstorms called guerrilla rains. These are basically torrential downpours. Because of the sudden rainfall, water levels rise quickly and the region is flooded.
To deal with the threat, the city has built the biggest anti-flood system in the world. Located about 30 kilometers north of Tokyo in the city of Saitama, it was designed to control and regulate river levels. Beneath the feet of these Japanese retirees lies a colossal structure that limits flood damage. The government-backed project cost over $2 billion.
The purpose of this facility is to regulate water flow to cope with the threat of flooding. We've built this system here to clear excess water. The system is made of underground tunnels, containment silos with pressure adjustment tanks, and pumps that can clear water quickly upstream toward the Edo River.
5 containment silos, 65 meters deep and 32 meters in diameter, have been built. They're connected by a tunnel over 6 kilometers long. During floods, excess water from the 5 rivers is caught and stored before getting pumped over into a huge tank. Here it is. Its dimensions are awe-inspiring. 177 meters long, 78 meters wide, and 18 meters tall. The structure is supported by 59 pillars. An underground cathedral that stores water to keep it from flooding the city.
Our pumps can clear 50 cubic meters of water, in other words 50 tons, per second. And we've got 4 of them. So in all, we can clear 200 tons of water per second.
The anti-flooding system can drain the equivalent of a 25-meter pool in 1 second. The water then gets pumped into the Edo River. Tokyo is pummeled by torrential rains and typhoons. The pumps work flat out and clear millions of cubic meters of water. The system has proven to be effective. Every time, Tokyo has been saved from flooding. But the brave city remains at risk to its #1 threat, earthquakes. Today, Tokyo is the city of superlatives. Over time, by combining tradition and modernity, the city has developed its might and forged a resolutely modern image. Tokyo boasts a wide variety of architectural styles, an entanglement of infrastructure, railroads, highways, tunnels, and skyscrapers. Opulence is everywhere. A vibrant city pulsating with energy, Tokyo is also a constantly changing urban landscape. Builders have one obsession: ensuring building durability while respecting Japan's anti-earthquake norms, the strictest in the world. The symbol of the city and its know-how is the Tokyo Sky Tree, a futuristic broadcasting tower standing 634 meters tall. The Tokyo Sky Tree was designed and built on the same principle as the 7th century pagodas. It's a flexible structure with a central pillar that can bend and shift during tremors. The movement does not impact the different levels of the building, which remain independent.
The sky tree is inspired by this. The heart of the shaft is very solid. The elevator is located right at the center. The floors where the people can move about are relatively flexible metal bars. The different levels move independently. It works like a damper or shock absorber against the wind and tremors.
The sky tree respects the essence of anti-earthquake structures to a T. It sways so that it won't break. But this system is not adapted to every building. In Tokyo, each type of structure has its own anti-earthquake system. For lower structures like housing complexes, Japanese ingenuity resides in the basement. They place large rubber cushions called earthquake isolators beneath the buildings. By separating the ground from the building, these devices absorb the shock from earthquakes. Efficient and simple, the system has become prevalent throughout the city. And yet, it is far from sufficient for the entire megalopolis. Due to real estate pressure, Tokyo has no choice but to build taller and taller buildings. But during an earthquake, a building's height is a decisive factor.
There are buildings of all sizes. They range from low buildings to skyscrapers. When there's an earthquake, what varies greatly is the oscillation period. In other words, the time it takes the building to shift from left to right, then back left again. The lower the building, the shorter the period. The taller the building, the longer the period. When the building oscillates, it's like waving a fishing rod. The tip of the rod moves the greatest distance.
What are the techniques builders have contrived in order to build higher on unstable ground? There's a whole art to building a skyscraper in an earthquake zone. The Mori real estate complex is the perfect illustration. With its 238 meters of concrete, steel, and glass, Mori Tower looms high over the Roppongi district, 53 stories, 6 basements. Its dimensions make your head spin, but the edifice is remarkably flexible when it comes to earthquakes. Its secret is hidden in its floors.
We're on the 52nd floor. This is where we find the shaking alleviation system, also called oil dampers.
In a more compact form, this sort of damper is also used in cars and high-speed trains to reduce shocks.
During an earthquake, the floors flex and move. While this movement is happening, the metal bars move from side to side. And this is where, thanks to the oil dampers, the movement gets absorbed. The valve moves from right to left, and the resistance of the oil slows the movement down and absorbs the shock of the earthquake.
The viscosity of the hydraulic oil enclosed inside the large pistons absorbs the shock waves. On either side of the damper, a special steel element absorbs horizontal stress and dissipates the energy. In the Mori Tower, there are 356 dampers like this, distributed among the different floors. The system is versatile and can absorb both small and large tremors.
This is the first building to incorporate dampers. They're the biggest ones currently available. They weigh 200 tons.
In this simulation, on the right is a classic structure without an anti-earthquake system. On the left, the Mori Tower with its anti-earthquake system. For the average building, we can see that the oscillation period, in other words, the left to right movement of the building, is much greater. The Mori Tower moves less, and on top of this, it stabilizes faster, reducing the amount of pressure on the tower's foundations. The entire complex is closely monitored from the control center located in the basement of the tower. 7 days a week, 24 hours a day, the building and its oscillations are scrutinized.
The building is outfitted with 5 accelerometers. We analyze the data from the accelerometers, and this lets us monitor tremors and the movement on each floor. We use the information to make efficient decisions after an earthquake. It lets us determine exactly where we should begin inspecting.
Today, the majority of Tokyo's large complexes and strategic buildings are equipped with sensors that analyze, record, and communicate the state of their walls, floors, and foundations. Besides offices, the Mori complex contains housing, and to satisfy residents, a new challenge had to be met: a huge rooftop garden on one of the buildings. An immense weight that could in no way compromise the solidity of the building. Their idea was to adapt the system of seismic isolators. The big rubber cushions are now used to hold up a garden.
Above this slab of concrete, there are 80 centimeters of soil, which allows us to have an actual garden. Here, there are about 40 rubber isolators that can bear the weight of the 3,650-ton garden. What's special about them is they are attached vertically and can move horizontally. We use modern tools to measure the movement, but to complement our measurements, we also use a primitive system, a simple needle that shows the tremors.
The scratches on this plate are evidence of the garden's movement and the instability of Tokyo's ground. Using the principle of energy dissipation, architects and engineers have demonstrated even more inventiveness. For instance, instead of being a handicap, a weight positioned above a building can actually help counter the effects of earthquakes. It's the principle of the pendulum. A mass weighing several tons is added to the top of a building. Like a pendulum, the mass opposes the structure's movements and dissipates the energy, which stabilizes the tower.
When the building moves, thanks to inertia, the weight placed up top absorbs the movement and limits distortion in the rest of the building. With a weight placed on top, when it moves to this side, it holds back in this direction and in the other direction. It's an efficient anti-earthquake method.
It turns out this type of damper works very well and can reduce the swaying of a building by 30 to 40%. It is becoming a general feature of new buildings. But what about old ones? Because although many new structures continue to be built in Tokyo, the city must also worry about adapting its older buildings to new seismic norms. In the district of Shinjuku, where Tokyo's first skyscrapers went up, the technological challenge consists of increasing the resistance of existing buildings without touching their structure. The solution: incorporating cross-bracing into the buildings, steel X-shaped structures.
We add cross structures to the walls. Then, when the building moves, the structures stretch and compress to absorb the shock. The building moves, of course, but in a limited manner. Without any resistance, the building would deform, whereas with the system, the tremors are quickly slowed. It's more reassuring for the people inside, and it limits the amount of damage sustained by the building.
For the past 30 years, Tokyo has deployed gems of inventivity to prepare itself for earthquakes. But until the late 2000s, it was impossible to know exactly how the structure would react in case of a major earthquake. Unfortunately, a dramatic event would truly put them to the test. March 11th, 2011, 2:46 p.m. Once again, the ground begins to shake in Tokyo.
I was at my desk, and my students were sitting beside me at their computers. Everything began moving. One of the students happened to have a camera handy, and he started filming.
An even stronger tremor had just occurred 380 kilometers away off the northeast coast of the country.
First of all, there was an impact, and the building began to shake. I knew we were dealing with a very powerful earthquake.
I told myself something very bad was happening.
Dubbed the Tohoku earthquake, for the name of the province closest to its epicenter, the quake was the most powerful Japan had ever experienced. The skyscrapers in Tokyo swayed for many long minutes, sometimes at an amplitude of 1 meter. On that day, in the basement of Mori Tower, operators observed the building's movements in real time. The red cursor reproduced the building's oscillations down to the very millimeter. Forward and backward, left to right, Mori Tower moved only 32.7 centimeters.
Up on the top floor of the tower, there's a restaurant. Well, thanks to the dampers, not a single bottle of wine was spilled.
Architects, engineers, and employees all witnessed the proper functioning of Mori Tower's earthquake-resistant systems. But in the north of the country, the situation was even worse. Off the Pacific coast, the earthquake displaced a large volume of water. A series of waves with large periods spread, provoking a tsunami. The wave loomed about 15 meters high and devastated the province of Fukushima. The death toll was dreadful. Over 18,000 people lost their lives. The exceptionally powerful tsunami caused the worst nuclear disaster of all time, the explosion of the Fukushima power plant. Further south, Tokyo once more managed to overcome the ordeal. The Japanese capital proved itself to be the most earthquake-prepared city in the world. But though its buildings stood tall, its inhabitants were left shaken.
Every system in Tokyo and the city's entire infrastructure shut down. There was no more transportation. Everything was blocked for 10 to 15 hours. A city of 40 million, and everything was stopped.
Transport, electricity, communications. The city was paralyzed. There's no question of ever letting this happen again, because an even greater danger potentially looms ahead for Tokyo, a mega earthquake even more devastating than those before. They call it the big one.
Look at this book. The Cataclysm of Tokyo is coming tomorrow. Tokyo's megaquake is a sure thing. Everyone says it's going to happen.
There's more than a 70% chance that within the next 30 years we'll be hit by a massive earthquake.
If the epicenter of the next earthquake touches Tokyo, that means it will affect a third of the Japanese population. 1/3 of the country's inhabitants live here. It will affect a third of Japan's population. The headquarters of every major company will be affected.
If Tokyo is hit, all of Japan will go down.
According to predictions, when the famous big one hits, between 1 and 2 million Tokyoites will be left homeless. Today, to prepare for the disaster, authorities have outlined major prevention plans. They've chosen to focus their efforts on observation and earthquake detection. Today, everything is in place to alert the population as quickly as possible.
When there's an earthquake out in the ocean, our sensors pick up the waves from the tremor.
An entire underwater observation network is in place off the shore of Japan. It helps determine the epicenter and the magnitude of the quake. A recorder at the bottom of the sea constantly monitors changes in pressure. An acoustic liaison then transmits the data to a buoy anchored on the water's surface. To be treated, the data is then beamed to a satellite which sounds the alarm.
The information is sent to phone service providers and to every media agency, such as the NHK.
People are alerted about the earthquake via their cell phones or television.
We warn people beforehand. If there's a warning, they must go and seek shelter.
The alarm has gone off. Now it's a matter of evacuating calmly and respecting the rules.
We imagine there would be 2 million people in the streets, and we simulate their evacuation. We have a highly accurate model of the city that can be analyzed with a complex program. The calculated study lets us evaluate at-risk zones and areas of congestion where people won't be able to get through. We can make calculations for the entire city of Tokyo.
Based on this data, certain buildings in every neighborhood of Tokyo have been designated as shelters in the event of disaster. These earthquake-resistant structures are called refuge towers. In the Roppongi district, Mori Tower is one of these emergency shelters.
If you live in an earthquake-resistant building, instructions are to stay put. But for tourists, shoppers, or people who live in the vicinity, they can come here. This is a safe building that can be used as a shelter, in keeping with an agreement made with the neighborhood.
Large stocks of food, water, blankets, mattresses, and first aid kits are stored in the basement of the tower.
We have provisions for 5,000 refugees. There's enough water, food, and first aid products to last 3 days.
Impressive, yet insufficient. For 1,700,000 people would still find themselves on the street with no place to go. Tokyo is working to create more shelters. What's even worse, if the big one does hit, an entire residential district in the northwest of Tokyo would find itself in grave danger. This area, called the Banana, consists essentially of traditional wooden homes.
In terms of traditional wooden structures, their ability to withstand earthquakes is limited, and that worries us.
For the Kanto earthquake, this type of wooden neighborhood caught fire. The consequences were disastrous. Unfortunately, a tragedy of this sort could very likely happen again.
Since the streets are so narrow, firefighters would have a lot of trouble getting in.
A program to fireproof the homes in the area as much as possible is underway. Some of the alleys are supposed to be widened to provide easier access for firefighters and ambulances. But homeowners are attached to their residences and like their neighborhood the way it is.
It's very difficult to establish new buildings in Tokyo. You see, all those old structures, all we'd need to do is just knock them down and build skyscrapers instead. But since people live in them, if just one person is opposed to it, then we can't. There are a lot of people who want to stay in the low buildings they've always known. So it's very hard to make things change quickly.
If the big one hits the Tokyo region, the bill would amount to 700 billion euros. The estimation sends chills down authorities' spines. Currently, they're trying to come up with new solutions to protect the city and reduce the economic impact.
Today, we're being asked to construct buildings that won't get damaged by major earthquakes and won't need to be evacuated. So we need to make advances in research and development to be able to meet people's expectations. For that, we're carrying out several experiments.
To obtain buildings that are even more solid, constructors are turning to building materials. And a small revolution is underway in the field. Recently, a French company has developed an innovative material that meets earthquake-resistant requirements. Here, in the National Building Research Institute, the capacities of the material are being tested.
Traditional concrete is made of sand, gravel, cement, and water. This new concrete is made of a powder that's equivalent to cement and a binder that iron fibers can be mixed directly into, very fine iron fibers.
Life-size components can be tested using this impressive machinery. Here, a foundation block is being assessed. An actuator on top of the structure applies pressure equivalent to the weight of the building onto the block. On each side, two other actuators simulate a horizontal tremor. Behind it, hundreds of sensors record the pressure on the concrete. On the right, the block coated with fibered concrete suffers very little damage. On the left, the unreinforced block breaks. This new material will allow existing buildings to be renovated in a way that gives them greater flexibility and improves their quality to resist over time. Builders have already shown an interest.
Today, the renovation market is bigger than the reconstruction market. And I think this trend is only going to accelerate. Before, our approach was to rebuild every 30 to 50 years. But nowadays, we're thinking more in the long term and more about the environment. That's the trend.
In the future, Japan's capital city fully intends to maintain its role as an influential city and major economic power on the world scale. But like most industrialized cities today, it is currently being threatened by pollution and global warming. Today, Tokyo must face up to an insidious danger, an invisible enemy, but one that is very present. The city suffers from a phenomenon called the heat island effect, and its skyscrapers are to blame. Heat given off by cars and factories is trapped by tall buildings, causing a localized greenhouse effect.
There's been an increase in the number of days experiencing intense heat, and the same is true for tropical nights, where the temperature remains above 25 degrees. We've observed this increase over the long term.
In Tokyo, the temperature has increased 4 degrees in the past 100 years, more than in any other capital in the world. This computer model shows heat distribution. Green corresponds to lower temperatures, red shows where temperatures are highest. The loss of green spaces and increase in number of buildings seem to be the culprit. To fight this new threat, Tokyo no longer has a choice. Tomorrow, the capital must shift into ecological gear and place its bets on green spaces. Green spaces that retain water, which lowers the ambient temperature when it evaporates. With more air and more parks and green spaces in the overpopulated residential zones, Tokyo hopes for better protection against the heat. A natural urban evolution that could also safeguard the city from a danger it considered to be a thing of the past: flooding. Because another consequence of global warming is the considerable rise in precipitation.
We're actually imagining the worst-case scenario. We've anticipated that by the end of the century, precipitation could double.
that point, the city would no longer be protected, and it would find itself underwater once again. Even the gigantic flood protection structure in Saitama would no longer be enough to clear the excess water. Engineers at the complex are concerned.
When we look at the data from the past 30 years for over 500 millimeters of rainfall per hour, we realize that, according to statistics, it's constantly on the rise.
Yet once again, the greening of the city seems to be a solution.
With more greenery, we can avoid guerrilla rains. These happen when temperatures are elevated locally. What's more, water will be absorbed better. And that, in turn, improves the environment. We need greenery. That much is clear.
Especially since in the city, public parks offer the best protection in the event of earthquakes. The transformation that Japan's capital has undergone in 100 years is simply amazing. Every time disaster struck, Tokyo has risen from the ashes. Just like its skyscrapers, Tokyo bends but doesn't break. In the future, like the reed, the city's inhabitants will continue to demonstrate humility and ingenuity. At this rate, Tokyo will be saved.